Hello world, this is the computer science man and we're back at it again. And today we're going to continue from where we left off from the previous lesson. In the previous lesson where we focused on converting denary to binary and binary to denary in the number systems. And today we're just going to look back at some key terms and we're going to solve some more problems for practice, conversion problems, and then we're going to move on to the hexadecimal number system. Before we start, I wanted to apologize for the delay in my uploads because I wanted to improve my audio quality, so I purchased a new mic. I hope the audio is more clearer and more understandable for you guys. Let me know in the comments if any more improvements have to be made. So, without further ado, let's get started. So, the terms I thought we need to go over once again is starting from bit. So probably from the previous level, a bit is basically just a single digit in the binary number system, which can either be 0 or 1, right? So it is based on the book definition, it's a digit in the binary number system written using either of the symbols 0 and 1. Okay, so this is just I wrote down the definition from the book so you can have a reference. And so a bit is like the simplest form. It's just one single digit. So if we want to group them together, we usually in binary we group them in groups of 4 or 8 or even 16. But usually 4, 8 is common. Okay, so nibble is just a group of 4 bits. A nibble, one nibble, exactly one nibble, is just a group of 4 bits. And a byte is a group of 8 bits. Okay, so usually all binary codes, what they call it, it's mostly written in the byte format, so which is a group of 8 bits. So a group of 8 bits is considered as like one unit. Okay, in this here when we use bytes. Okay, from bytes we'll go move on to that's when we'll learn the binary prefixes, and that will be in the next lesson. So before we go to all to that, we need first focus on understanding conversion between these number systems. As you can see in the syllabus, we need to know how to use the binary, denary, and hexadecimal number bases before we go into anything. Okay, I mean, yeah, but first they have written the prefixes here, but I think this is a better route than that. Okay, so let's go on to practice. Okay, so the first two questions I will do it, and the last question is for you to solve it, which I will reveal the answer sometime later. So first we'll start with this nibble number, or nibble type of number, or 4-bit number. In binary, so we need to convert this to denary. So what do? I'm going to use the tabular column method. So I'm going to use a different color. I'm going to use, okay. So the tabular column method, 8, 4, 2, 1. And if you remember from the previous lesson, these are just the base 2 raised to the powers based on the placeholder position. So this is 2 to the power 0 because this is the first position. We start from 0 in these number systems, by the way. So 2 to the power 0, 2 to the power 1, 2 squared, and 2 cubed. That's what it represents. So just to let you know, that's why it's base 2 number system. Okay, so we can write 1, 0, 1, 1, right? So what is that? So that's 8 into 1, which is 8 plus 2, plus 2 into 1, plus 1 into 1, plus 1. So that is 11. So 1, 0, 1, 1 in binary, which is a nibble. It's known as, nibble as in because there's 4 bits used to represent this number, so that's 11. If we convert it to denary, okay, let's try one more. This is an 8-bit number, okay? So that means we go from 2 to the power 0 all the way to 2 to the power 7, 0 to 7, right? So that means that'll be 1, 2, 4, 8, 16, 32, 64, and 128 binary. Okay, so this is an 8-bit tabular column for conversion. Okay, so 0, 1, 0, 1, 1, 1, 1, 0. That means that 64 into 1 is 64, plus 16 into 16, plus 8, plus 4, plus 2, right? So am I correct? 0, 1, 0, 1, 1, and 1, 1, 0. Yeah, that seems to be correct. 64 plus 16 plus 8 plus 4 plus 2. So 64 plus 16, it's 80. 80 plus 8 is 88. 88 plus 4 is 92. 92 plus 2 is 94. I'm pretty sure I'm correct. Let's check it out again. 64 plus 16 is 80. 80 plus 8 is 88. 88 plus 4 is 92. 92, yeah, 94. So that is how you convert a binary number to denary. The other method I thought you was, yeah, this is the method I thought you. Okay. I mean, the other method was for the binary to denary, where you can use the long division one, but I prefer the tabular column compared to that. Okay, so this question is for you. I will show you the answer at the end of the lesson, so I'll leave this question to be solved by you. Okay, so now we're going to move on to converting from binary to denary. From denary to binary. So it's 85. So that means remember when we learned that, in a 4-bit or nibble number system, it's usually not usually, the maximum denary number that can be represented by a 4-bit number it's 15, right? So we can, there's one method, we can just put all ones here in the 4-bit number system, and if we add them all together, we get 15. Or there's one more method. So since it's a 4-bit system, what you can do is, let's say, one second. So max denary number represented by a number of bits. So remember, we said for a 4-bit number, that means the maximum denary value we can represent is 15. So that's 15 minutes. So the math shortcut here is you need to raise 2 to the power of whatever the number of bits you're using. Like, you're using 4 bits, right? So 4 bits, 2 to the power 4 minus 1. That is 15. So you can, with this equation, so instead of here, the 4, it could be a variable, okay? So 2 to the power x being, it's just the number of bits you're using in the number. So for 7, it's 2 to the power 7 minus 1. Sorry, for 8-bit. We need for 8-bit because we're doing 8-bit right now. So for 8-bit, it's 2 to the power 8 minus 1, which is 256. 256 minus 1 is 255. So the maximum denary value you can be representing an 8-bit number is 255. Okay, so that means we can use an 8-bit number system to convert, 8-bit number to convert 85 to binary. So I'm going to write 128. 64. I mean, yes, you can use a 7-bit number system, but usually we like to keep a format, and typically we follow 4-bit or 8-bit. So most commonly, so I'm gonna just follow an 8-bit. So 128, 64, 32, 16, 8, 4, 2, 1. So sorry, let me write that again. Okay, so we start again with the largest place value, so 128. We check if it's if 85 is greater than this, no, or equal to, no. So we put a 0. If it is, we put a 1. So 85 minus 64. So 85 minus 64, if you do that, you'll get 19, right? So let's check with 30. Sorry, not 19. You'll get 21. Okay, so 21 is the answer. So 64, 32. That means, is 21 greater than or equal to? Nope, it is not. Then 16. Then we have remaining is 5. So we get 0, 1, 0 1 0 1. So converted to binary, it is 0 1 0 1 0 1 0 1. So 85 0 1 0 1 0 1 0 1. That is what 85 is. Okay, so same as for this binary number, you need to convert this binary number to a binary number in using the 8-bit numbers, using the byte format. So I will again show you the answer at the end of this lesson. So now we'll move on to the hexadecimal number system. So hexadecimal, we have looked at base 10, which is DNA, which is what we use in everyday life, and binary is base 2, which is what computers use like underneath the hood, the on and off switch kind of thing. And here hexadecimal, this is a base 10. So this, sorry, not my bad, a base 16 number system. Okay, so now you may be wondering, in base 10 we said there was 0 to 9 digits, which is 10 digits, and in base 2 there's 2 digits, which is 0 and 1. Here this 16, there can be a possible of 16 digits. So here's the interesting part. So how the digits we can, or digits or characters we can use to represent in a hexadecimal number system is, so starting from like same as the binary, you can use 0 to 9, which represents 0 to 9. Okay, just the actual 0 to 9. So from 10, through 15, okay, which is inclusive, 10 to 15, which is inclusive, we represent these numbers, I mean 10, 11, 12, 13, 14, as, sorry, represent them as A to F. So from 0 to 9, the same old denary numbers, but from 10 to 15, so 10, 11, 12, 13, 14, and 15, we represent this as A, B, C, D, E, F. So this is the hexadecimal number system. These are just the characters we use to represent numbers here. And so now you may be wondering, how the hell do we convert a binary number or a denary number to an hexadecimal number? Well, it's actually not that hard, you can see. So hexadecimal basically is represented by, it can be split. So hexadecimal, usually we use the nibble format. Okay, so a nibble can be represented by one hexadecimal digit. So one hexadecimal digits, one hexadecimal digit is a nibble. So let's say for example, okay, let me write an 8-bit number. So you have to remember one thing before I continue. Usually for hexadecimal, given a binary number, we split it into groups of 4. As I said, one hexadecimal digit is a nibble. So we split it into groups of 4, and we then convert, based on that group of 4, since we have 0 to 15. And remember, in a nibble, the maximum denary value that represents 15. So based on that, we just write the hexadecimal digit for the respective number. So let's say you're given the nibble 1 0 1 1. So what did we see this was? This was 8 plus 2 plus 1, which is 11. So this is 11, right? So what is 11? 11 is B. So the binary number and denary number 11, so binary number 1011 and the denary number 11 in hexadecimal, so this is binary, denary, and in hexadecimal it is B. Okay, so it is represented as B. So if you're given like let me say you're given a 16-bit number such as 1011 0 1 1 1 1 1 0 0. Okay, I'm gonna make it actually not 16. I'm gonna make it 20. Okay, so let me just add one more. 0 0 0 1. Okay, so if you're given a number like this, the first thing you do is split it into groups of 4. So you just split it to groups of 4. That is the uh, that's the fundamental thing for hexadecimal. One hexadecimal digit is a nibble, so it's 4 bits. Okay, well, after you split it, you can just look at the value of this. So 1011 is 11, which is, so we just write this as B. 0111, which is 4 plus 2 plus 1, which is 7. 7 is just 7, right? So it's just 7. 1100, which is 8 plus 4. Wait a minute. Yeah, sorry. It's 8 plus 4, right? So it's 12. That means it's C, right? Because 12 is C. And then 0001, which is 1. That's just 1. So this entire 20-bit number is written as B7C1. Oh, wait. Let me just clarify that. Previously I said when I wrote 3 nibbles, I said it's a 16-bit number. That is my bad. It is indeed a 12-bit number, and now it's a 16-bit number, not a 20-bit number. That is, I apologize, that is actually my bad. Okay, so B7C1 is this represents that huge 16-bit number, which is in binary. And if you convert this to denary, it's going to be bonkers. It's going to be huge, humongous. Okay, so that's one of the major advantages of hexadecimal. It takes up less space on the screen, so that's one of the major advantages. It takes up less space on the screen. It's easier to read compared to whatever this monstrous digit number is in either binary or denary. And so that's why they usually use it in error codes. So for example, I've taken a screenshot from the Microsoft page. So for the error print cancel. So for example, you're sending the printer a file to be printed, and while it's processing, before it starts to print, you just delete that file. Before the computer sends the data to the printer, you just delete that file. So when that happens, you will probably receive the error code 0x3f. So this 3f part, that is hexadecimal, right? So we also use hexadecimal in error codes. So we use hexadecimal number system, hexadecimal numbers for error codes. That's another use of hexadecimal. So it takes up less space. I think it's also used in MAC addresses. I'm not sure. I'll look into that once. And yeah, that's it. So this is how you can just convert it from binary. So from denary, what you do is you first convert to binary. You take a format that's can be easily divided into four groups of 4 bits. Okay, so yeah, so if you have a denary number, you convert it into binary and to an 8-bit, 12-bit, 16 bits, 4-bit, so on and so forth. Sorry, 4, 12, 4, 8, 16, 20, and so on and so forth. Right. So if you're given a hexadecimal number, such as A1F, okay, you're given this number. So how do you convert this to let's say binary? So again, the same thing. A is what? A is 10, right? So you can just write the nibble version of this number, or the 4-bit version of this number 10, which is just 1010. So 8 plus 2. Okay, 1 is just 0001, and 15 is F is 15, so 1111. So you can just stitch these three groups of 4-bit numbers together, and that is the binary number that was written as an hexadecimal number. And let's just say they want you to convert this to denary, so you just take the further step of doing the tabular column method and finding the number for denary. So that's about it. And yeah, so today what we learned was, the binary number system, and we did the hexadecimal number system, and we did some revision of the some terminology, and we had some practice. So yeah, that's about it. And yeah, here are your answers. These are your answers. You can check them. Yeah. Thank you, and I will post my next video by tomorrow. So I'll see you later. Thank you.